Hello everyone. In the previous video, we talked about the basics of spectroscopy, what spectroscopy is, what is the importance or the need of spectroscopic tools, and we talked about the electromagnetic radiation being composed of oscillating electric and magnetic fields, and we talked about the electromagnetic spectrum as well, and we talked about various terms like wavelength, frequency, etc. So this is the electromagnetic spectrum, wherein we have the radiations varying from gamma rays through X-rays to radio waves. So wavelength is increasing as we move from left to right, and the energy is decreasing. And the type of energy we are focusing on today is the infrared light. The infrared region is further divided into three regions. Near infrared region, that is the one which is closer to the visible seven colors, and then the mid infrared region and the far infrared region. Of these three regions, the mid infrared region is the region of interest for us as organic chemists. Why is it so? To understand the why behind this, we need to understand that it's not only light which has the dual character, that is the particle and the wave character, but also matter. Matter also has dual character. It has a wave character as well as a particle character. So there is an inherent duality in light as well as in matter. And according to the principles of quantum mechanics, so quantum mechanics tells us that the energy of the molecules or matter, for that sake, the energy of the molecule is quantized. Energy of a molecule is quantized. What does this mean? It means that it would have only certain allowed values quantized, and not all the values are possible. Like there is not a continuum of energy. So suppose there's a molecule and it has a possible energy levels E1, E2, E3. So there are allowed energy levels and energy is quantized. A molecule, suppose at a room temperature, a molecule is in this state of energy, okay? By absorbing exactly this much amount of energy, like which is equivalent to this gap, that is delta E, the molecule can move from E1 state to the E2 state. But if energy gap, which is delta E, if the energy which you are supplying to the molecule is less than this delta E, then the molecule cannot come here or there. It is not allowed. So the energy levels are not like a continuum. No, they are quantized, and there are certain gaps between the energies, and if that energy gap is catered by the exact same amount of energy, then molecule can go from that energy state to the other energy state, right? So the molecules can store energy in various forms. They can store energy as, because they can do rotational motion, so as rotational energy, as vibrational energy, and in their bonds as well, right? Now, talking about particularly the infrared spectroscopy, it is also called vibrational spectroscopy. So the infrared light is not that strong that it can break a bond between the atoms. Suppose we have a molecule AB. So if I irradiate this with infrared light, so the energy of infrared light is not that much that it can break this bond, right? What instead it can do is, it can bring excitation in this bond, in terms of, like, if you think of bonds as springs, like this, if you think of them like they are like springs, then infrared light can make it vibrate into a higher energy level, right? Suppose this is the fundamental frequency of vibration, that the molecule is vibrating, and this line represents its energy at zero state, say, and vibrational energy level 0. Now, by absorbing energy, it can go to 1, right? So this much energy gap, which is between these two vibrational energy levels, This gap mostly falls in the IR region, that is, the energy of infrared rays is enough to cause this excitation, and the energy of infrared light which is absorbed, we try to calculate or observe like what wavelength is absorbed, and based on that we can find out what is the functional group present in the molecule. Now, since we talked about springs, so for springs, the law which is there, which is that is Hooke's law. Springs, the frequency for the frequency of vibration of a spring, Hooke's law is used, which tells us that nu is equals to 1 divided by 2 pi under root k by mu. That is, the frequency of vibration of a spring is equals to this thing, where k is the force constant. K is the force constant of a spring, and to visualize that you can think of it as the stiffness of the spring, like how stiff the spring is. And for chemical bonds you can think of them as bond strength, how strong the bond is, right? So it varies from bond to bond. And mu is reduced mass. Mu is reduced mass, where reduced mass is nothing but m1 m2 divided by m1 plus m2. That is, if you have only one thing, okay, so the spring is suppose connected to this, then you take the mass of the atom to which it is attached. But since for diatomic molecules, when we are talking about the diatomic molecules, so both the atoms are involved in this. So in case of reduced mass, we treat this diatomic atom as a single entity, and this is how it's like a single entity. So now what does this equation tells us? Hooke's law, it tells us that the stronger the bond is, the more would be the frequency of vibration, right? The other thing it tells us is the more the mass is, the greater the reduced mass is, the lesser would be the frequency of vibration, right? So why we talked about Hooke's law here for the springs? Because we are going to treat the bonds between the atoms as springs, right? Now, there are various modes of vibration. So we are talking only in terms of like, not we will be talking about the polyatomic atoms, but there are mainly two modes of vibration. Stretching and bending. Stretching and bending. Bending vibrations, stretching vibrations. Stretching requires more energy as compared to bending. So stretching vibrations appear at higher frequency. So they require lesser energy. Stretching vibrations are of two types: symmetric and asymmetric stretching. Asymmetric stretching. Asymmetric stretching. By symmetric stretching, we mean like if you consider your body as carbon and your two arms as hydrogens. So you can stretch out so this is suppose carbon, and these are the two hydrogens attached to it. Suppose this is a CH2 group. Then they can stretch like both of these. So both of these can go out like along the bond length, along the bond line. They're not going away. So this is symmetric stretch. Okay. Or the other possibility for these is that both of them, they're coming like towards the carbon. This is also symmetric stretch. For asymmetric stretch, one of the bonds, like this is hydrogen, this is again a hydrogen. So one bond is moving away from the carbon, the other one is coming towards it. So this is an asymmetric stretching. So these are the two modes. Or it can be the other way around, that this one is coming this and this is going away. But it is always along the bond length. Along the bond length is like along this bond axis. So the bond axis, it's not going to leave that, it's not going to bend, it's not going to twist. that comes under the bending vibrations. So bending vibrations are further of two types: in plane bending and out of plane bending. Out of plane bending. For in plane bending, we have two types of movements further: scissoring. Okay, what is scissoring? Just like the two blades of scissors, so if this is a scissor, so when you cut it, one comes here, the other one, they approach each other. Okay, that is scissoring, right? Then the other one is rocking. Just like the rocking chair, the both the things, they go in plane, back and forth, right? That is rocking. Out of plane bending, we have twisting, like one is going, like you twist the things going out of the plane, right? They go out of the plane in twisting. I can show the twisting here. Twisting is like you have carbon, you have hydrogen, you have hydrogen. So this goes, suppose, like this, and this is going like this. So this is twisting. And then we have wagging. Wagging is like you have this thing, they are out of plane again, but they are moving in the same direction. Okay. Now these were the different modes of vibrations of different bonds. Now I want to tell you that since the energy levels, they are quantized, so it also depends upon so when you plot the IR spectra, you plot the IR spectra between the wave numbers, like the wave number is on the horizontal axis. Units for wave number are centimeter inverse. And on the other side, that is the vertical side, you have percentage transmittance. Right? That is what you have. So percentage transmittance is there. Just a moment. So you have percentage transmittance here. Right? And this varies from 400 to 4000. And I will make a separate video of how to decode the spectra. Right? To read the spectra, you always read it from this side to this side, from left to right, right? And the type of signals which you observe in the vibrational spectrum, they are called peaks and bands. So they can be like this: sharp peaks, intense peaks, depends upon various factors, right? So this was, so suppose this is one vibrational level, this is another vibrational level, this is the third vibrational level. So this is, suppose, for the carbon hydrogen bond we are talking. So it changes from bonds to bonds, and you have a carbon oxygen bond. So it may be possible that the gap between the first level and the second level is lesser for the carbon oxygen and higher for the carbon hydrogen bond. It depends upon bond to bond, right? So this was all about the principle of IR spectroscopy. To summarize, I can say that when you shine light, infrared light, on molecules, they start vibrating at a higher frequency. They on absorption of infrared radiation, they move from one vibrational state to other vibrational state, and we use this information, like which IR frequency is absorbed by the molecule. That gives us the information about the type of the functional group present in the molecule. Thank you.